Okay, so everyone, welcome to today's seminar. I'm announcing it from a slightly awkward place because of the sound system. Raghav also hear us. So we're very happy to have Raghav Jha today for a seminar for the people who were at our school, the MITP school in the University of Pretoria. Raghav delivered a very nice set of lectures and intensive lectures there. And today he's giving a seminar about recent work on the SYK simulations of the SYK model on a quantum computer. So thanks a lot, Raghav, for agreeing to give a talk, and please take it.
Okay, thank you so much, Sam, for the introduction. I would have been there in person, but due to visa problems, I could not make it. But hopefully, I'll be able to talk about some work I've been doing over the past 6 months or so. So today, I'm going to talk about this paper we wrote with graduate student at Syracuse, and now another student, Asad, who started his first postdoc, which is related to the SYK model, which is a very popular model. I'll explain what the model is, why is it interesting, like sort of argue why is it interesting, and then show some results we obtained using IBM quantum computers. And then I'll also touch upon some follow-up work we are doing to prepare thermal states for the SYK model using variational algorithms. Okay, so first of all, let's see, I have to move this cursor somewhere, so let's move it here. Okay, so the first thing I want to say is to understand why we really need to do quantum computing. So one of the motivations to do quantum computing is to understand or to solve problems which are exponentially hard for classical computers. So for example, when we talk about classical information theory or classical complexity theory, we divide problem into various classes. So some of the problems are in P class, which you see here in the green circle. Then there are some problems in the blue range, which includes NP and NP complete problems. So NP and NP complete problems are problems which are exponentially harder in system size, basically, or as you increase the number of points or number of degrees of freedom for a classical computer. Those belonging in P, shown by green, can be solved efficiently by a classical computer, right? But there are a lot of problems we know which are in NP or NP complete. And those problems cannot be solved efficiently by computers which we have today, even the biggest of supercomputers. And for those problems, people realize eventually in the 80s, 70s, and the 80s that there has to be a new shift in paradigm of thinking about computing. It's not about building better computers or having more transistors on your chip. It's about completely different approach to computing, which exploits something which can help you solve problems which are otherwise hard. So for that, quantum computing can be useful. And one of the important classes of problems where quantum computing is actually useful is problems which belong to NP but do not belong to P. And those are what we call as bounded quantum polynomial, BQP. It's bounded quantum polynomial because it can be solved in a polynomial time by a quantum computer with a bounded error. So whenever we do a quantum computation, you have to say that, okay, this is the error I want to tolerate, how hard it is. And those problems are sort of belonging to the class which is called as BQP. You might have heard one of the very popular algorithms known as Shor's algorithm, which is supposedly an algorithm which will help us factor big prime numbers using quantum computers. Those sort of problems belong in BQP because they're hard for classical computers but efficient for quantum computers. So one of the misconceptions which I just want to get away, just flash at the start of my talk, is that quantum computing can solve all problems. It cannot solve all problems. So for majority of problems, quantum computers would do no better than classical computers, because if you add the overhead and actual speed up due to quantum algorithm, it's not much better than the classical algorithms. But certainly for some problems, it's going to be a game changer. For example, for factoring in prime numbers, for example, for quantum simulation of many body systems in physics, or for time evolution. For example, if you want to do a real-time scattering or say interacting phi for theory in 1+1 dimensions, it can be solved efficiently by quantum computers in the sense that it belongs to BQP class. It is exponentially hard for classical computers if you say increase the system size, and so on. So these kind of problems are interesting for us. There are a lot of time evolution problems. For example, time evolution of Bose-Hubbard model, Hubbard model. These problems are also known to belong to class of problems that are well suited for a quantum computer, right? There's another algorithm which you might have heard is known as Grover's algorithm, which is like a search algorithm. So suppose you have a list of numbers going from 1 to n. If you ask the best classical algorithm to find some number from that list, it will take order n operations. Whereas using Grover's algorithm, you can get a polynomial advantage, and you can solve this problem in order square root of n. Right? So it's not as nice as Shor's algorithm, because Shor's algorithm is exponentially faster than the fastest classical algorithm, but the Grover's algorithm is only polynomially faster. So polynomially faster means if something is going like n square, quantum computer is going like n. But for exponential, it's much more prominent. So ideally, one would like to have exponential advantage, but it's not very easy to find such problems. We only know some problems. So the outline of the talk is this. I'll just flash a couple of slides using the state-of-the-art methods we have right now, using classical computers, which are known as tensor networks. And then I'll talk about how we can look at quantum many-body systems using quantum gates and quantum computing, and show you how to do the real-time evolution using quantum circuits, for example. And then I'll explain the SYK model. And then in that model, you have you have a parameter which is called n, which is the number of fermions or Majorana fermions. And I'll show you some results with 6 and 8 fermions on IBM quantum computers. Just to make it clear, the current state of the art classical computers for SYK model is about n equal to 60, 65. And n equal to 8 is the best we can do on the quantum computer. So we are still way away from the quantum advantage or doing something which classical computer cannot. But this is a good start we made on this problem, and this is interesting because of various reasons. And then I'll talk about the summary and some future directions. Okay. So for tensor networks, we can have Hamiltonian picture, or you can have the Lagrangian picture. So for the tensor network picture, let's look at the Hamiltonian approach. So the Hamiltonian approach just says that suppose I have n spins, and each of the spins can have a local Hilbert space of dimension small d, which is written here. So how can I efficiently describe this state of this system of n spins with some local Hamiltonian? And it turns out this is an exponentially hard problem, obviously, because the size of the Hilbert space is 2 to the n, or d to the n. And d to the n becomes unmanageable for n which is more than 50, for example. So if you have, say, 100 spins, you cannot write down the state exactly on the biggest of supercomputers we have today. So tensor networks is an approximation where you map or change that exponentially hard problem into a polynomial problem. In fact, a problem which is not even scaling with quadratically with n, with just linear in n. And how do you do that? You use the fact that not all the spins are entangled with each other, or the system is slightly entangled. So if the system is has if you are trying to find out the ground state of a system with local Hamiltonian and it's gapped, then the ground state is not severely entangled. It's very slightly entangled. And in that case, you can make an approximation by replacing the upper diagram, which is the actual and needs exponentially large Hilbert space, by the lower diagram, which is the tensor network diagram, MPS approximation, where you say that I introduce some fictitious intermediate bound dimension, which is given by chi, and then I don't take chi to be very large, but some small number, and then only let the neighboring spins interact in certain, which is determined by how big chi is. Obviously, if you take chi big enough, you can go to the actual description, but you don't need chi a lot. So this is what I talked about in the summer school, how to deal calculations with these tensor networks. So this is the best classical algorithms we have today. So this was the Hamiltonian picture. Now we come to the renormalization group, or the partition function picture, or also I call it the action picture. So before, if you want to study a quantum Ising model, you use MPS method. If you use some quantum spin system, you use that. But say, for example, I want to work with some Euclidean lattice field theory. I have some action, say Wilson action, QCD, SU2 Wilson action, SU3 Wilson action, or I have some Heisenberg model, ON Heisenberg model, or some nonlinear sigma model like O2. How do we study that using the partition function picture? So there are a lot of progress made by initial work in 2006 by Levin and Nave. They wrote a paper, influential paper, which started this field, inspired by, say, DMRG and other stuff which was done in the 90s. And what this really is useful for is that, for example, when Monte Carlo methods fail, for example, when you have a sign problem, or for example, you have a theta term when the action becomes complex, the Monte Carlo methods cannot be used. And that is a big headache, because eventually one day we want to understand the QCD phase diagram at finite baryon density. And for that, we really need some other tools, numerical tools. And tensor network promises to be one such tool. So this is still classical picture. There's nothing quantum about what we have discussed. So these are classical algorithms, MPS, TRG. These are classical algorithms which makes use of classical computer to solve quantum and complicated many body problems. So the basic idea of TRG is that you start with some description in terms of tensor, which is based on the character expansion, or from lattice gauge theory, the strong coupling expansion of the action. And then you rewrite that action in terms of characters of the group, or in terms of weights of the tensor. And then you coarse grain that tensor under some approximation. It's not exact RG, because obviously it's very difficult to maintain exact RG, because the degrees of freedom have to be gets so big that you have to put it on a computer. So you have to truncate at some point. But if you do those truncation procedure reasonably well, and that is all we try to do in TRG, then you can reproduce the fixed point behavior or the critical phenomena pretty accurately. And you can compute, say, for example, thermodynamic observables like free energy, energy density, and whatever you want to do. So this is an alternate approach in which I have also been associated with, because my research is mostly computation from both classical and quantum point of view. And for classical, we use tensor networks, TRG, MPS. And for quantum, we use what I'm going to talk about in the later half of the talk. So we got some interesting results in 2D SU2 gauge theory, S3D O2 model. We found some phenomena which are very hard to find using Monte Carlo results. For example, we computed the potential of from the Polyakov loop correlators. We also looked at some phenomena at finite chemical density, or sorry, chemical potential mu. And you can read these papers and about all this work. But these are not what I'm going to talk about today. Today I'll mostly focus on going from the classical to quantum. So tensor networks, which I flashed in the earlier slides, can be used in lower dimensions. So for example, 2-dimensional Euclidean, or even in 3-dimensional Euclidean. But as you go to higher dimensions, the prescription of this tensor denormalization group becomes harder and harder, in the sense that the approximations become uncontrolled. And eventually, if you ask me, can I use MPS to study scattering in 3+1 dimensional quantum Ising model? Then probably the answer is no. We cannot go beyond 1+1 dimension in, say, real-time dynamics using tensor networks, because preparing a ground state is different thing, and then doing a real-time dynamics is different thing. So some of them might be easier, some of them might be hard, depending on circumstances. Usually time evolution becomes harder because the entanglement grows and so on. So we need a new idea of computing, which was proposed by Manin, Benioff, and Feynman around 78. And the basic idea was that, suppose I have a given Hamiltonian, how can I exponentiate it? So the entire quantum computing can be, like, at least for physicists, it can be said that you prepare a state, some state, and you do time evolution. So how do you actually exponentiate this? This is a exponentially hard problem for a classical computer, because as you increase the system size, the h increases exponentially in the system size, right? So if I really want to exponentiate this operator for some Hamiltonian on a, say, in the thermodynamic limit, it's completely hopeless for a classical computer. Maybe the hope is that maybe with quantum computers, we can do this efficiently, because the scaling in h will not be volume dependent, but it will only increase in the number of qubits. For example, if I take 50 qubits and I have 2 to the 50 Hilbert space, if I take 100, it's 2 to 100, but the number has only increased by a factor of 2. So it's not exponential in the system size. So there are various approaches to quantum computing. The one you might have heard, the qubit-based approach, is the most popular, which manipulates and utilizes a two-state system. There are more than a dozen approaches, but the two most popular one are, I think, superconducting qubits, which is developed by IBM. And there's also one based on trapped ion, developed by companies like IonQ or Quantinuum. There's another approach, less well known, is the approach using Q modes, or the approach using photons, for example. Photons are not two-state systems like we see for qubit. Qubit can either be up or down. It's a two-state local quantum system. But one of the famous examples which we study in quantum mechanics course is the harmonic oscillator, and it has an infinite dimensional Hilbert space. So people have also been trying to use Q modes or photons or harmonic oscillator states to do universal quantum computing. And that is also an approach I'm associated with. So we wrote a paper on 2D nonlinear sigma model. Now we are looking at SU2 Kogut-Susskind Hamiltonian using this approach. So this approach, the basic idea of this approach is that everything is oscillators, right? So you take your Hamiltonian and then you try to rephrase it in terms of oscillators. You might need different number of oscillators at each side to actually map that Hamiltonian. And that is what this does. How many oscillators do you need? How do you truncate the Fock states? How do you manipulate those states? How do you do time evolution, things like that? And that is the CV approach, which also I'm not going to talk about. I'll just focus today on the superconducting qubits approach to state quantum systems. There are a lot of companies, as you can see here, related to all this I have talked about, which is on the right side. Superconducting, as you can see, there are more than a dozen companies. Then there are a lot of companies using trapped ion, and there are a lot of companies now using photonics. And there are other approaches like neutral atoms, cavity QED. Topological qubits is the one popular method approach people are also exploring. So since you might not be that familiar with the CV approach, I'll just quickly flash this comparison. The basic elements is Q modes in CV, it's qubit in the qubit approach. The relevant operators is the sigma Pauli matrices for the qubit approach, while for CV, it is the quadrature operators of the harmonic oscillator X and P. or the mode operators A dagger. The common states in CV is coherent states, squeeze states, number states, which we all study in quantum mechanics when we do oscillators, harmonic oscillators. While in the qubit language, it is the computational basis 0, 1, plus minus I. There are different unitary gates for CV formalism, which is rotation, displacement, squeezing. And for qubit, you have gates like phase shift, Hadamard, and so on. Okay. One of the important things which we need to keep in mind when doing quantum computation is this theorem. This is a no-go theorem known as Gottesman-Nil theorem, which says that there are some quantum circuits. So it's not sufficient that you have a quantum circuit and you can do it well, and then you can do some computation which is impossible for a classical computer. This theorem says that there are certain circuits, for example, circuits which have certain gates, which are, say, the H gate. I'll talk about what H, S, and C naught is in the next slide. So if the circuit is made up of some gates like H, S, C naught, it can still be simulated classically in polynomial time. So there's no advantage if you just have a quantum circuit and you give me a circuit made up of these gates. There's an equivalent statement in the CV language as well, which says that you need to have some non-Gaussian operators to achieve universal quantum computing. And people do that using, say, photon detection or some other non-Gaussian gates. And if you have any of these things, then you achieve universality. By universality, I mean that any computation can be done in terms of those gates. So it's like the universality of the classical computing when we do NAND gate, NOR gates, AND gate in Boolean logic. We say that some gates are universal. It's exactly the same thing, just that now everything is quantum. So what is the discrete gate set? For example, I talked about here about H, S, and C naught. So H gate, for example, is shown here in this. Yeah, it's bad that I cannot point it, but it's okay. It's the fourth one from the top. It's called the Hadamard gate. It has a matrix representation. Then you have the phase gate below it, S and P, and it has a matrix representation. Then you go all the way down and you have control naught or C naught gate, which is given by this representation. Note that if you have a gate and you represent the gate by some letter, say X, Y, Z, H, S, and if there is just one wire, it's called a 1-qubit gate. If it has 2 wires, it's called a 2-qubit gate. And if it has 3 wires, like the Toffoli gate you see at the bottom, then it's a 3-qubit gate. So every quantum operations can be described in.
We can actually see, we can't see your cursor.
You cannot see, sorry, what? Wait.
We can see your cursor. You can point with it. It's not his cursor, it's the other cursor. Oh, there are 2 cursors.
Okay, no. Okay, sorry to interrupt you. No, we thought we could see your cursor, but it turns out that was actually the cursor of the computer.
Okay, okay, no problem. Yeah, it's fine. I don't really need cursor. I'm leaving this. Yeah.
I think it was clear, the gates. Okay, please.
Okay, thanks. So let's see, I can go back here. So yeah, these are the gates we have. Then you can have states, for example, which is shown on the left. So you can start with a state which is, say, on the north pole of this sphere, which is the 0 state. Then you can go to the other end or the south pole of that, which is the 1. And then you can create superposition states. So for example, one of the superposition state, uniform superposition state, is denoted by plus state. And plus state is nothing but a uniform superposition of 0 and 1. And it's given by this. So how do you go from a 0 state to a plus state? You just do a Hadamard. So if you do a Hadamard gate or the H gate on the north pole, you get an equal superposition and so on. So these gates can manipulate the quantum states, and that's all it is. Prepare the states, do unitary transformation. Each of these transformations are unitary, so we can do these operations without a problem. So are there any questions at this point?
Yeah, maybe I can ask a question. So could you so some easy way to see why this, if you add in this T gate, then things cannot be simulated.
Yeah. There's no easy way I know to see that actually. The fact that so this was studied, so there are different set of universal gates you can have. So for example, you can have other set of gates which are, say, you can take Hadamard and Toffoli, and that is also universal. But uh, just adding a T gate to Clifford group makes it universal. That we know that it makes it universal. There are proofs for that, but I don't know of an easy way to explain that. But one of the ways, okay, so the problem with this H, S, and C naught is that if you use these gates, you only get two states which are called stabilizer states. So suppose I start from a state where all the spins are up, and I make a circuit consisting of just these states, then you cannot reach all the states in a of the Hilbert space, for example. There are some states, it's like you can reach the integers, but you cannot reach all the real numbers or something like that. The spacing is not that much. But if you add T gate, which is like a square root operation of the S gate, then it's in the square root operation of that gate, which actually, so it's sort of related to the fact that something is rational and something is irrational. For example, square root of 2 is irrational, right? So we can ask that 2 is rational, but if you square root it, it's irrational. So it's going, yeah, somehow this S gate, addition of T gate makes it, you are, it allows you to obtain all the states, I think. I think that is the short explanation I can give.
So this is actually a good question from Sam. Is it not because if you include the T gate, then from the Hadamard C naught and T gate, you can then also build a Toffoli gate. Then from that, you will have a universal set. Because you just need, I think, yeah.
Okay, I think, Raghav, you can hear me now. You can hear me now.
Yeah, I can hear you. Yeah, better, yeah.
So would it also be a universal set if I just add the following Z to the Hadamard S and C naught? Does that also form a universal set?
So sorry, you are saying that if you just add poly matrices to Hadamard and C naught.
Yeah, just the Z, say just the Z value.
Yeah. I think that is also a universal set. So rotation plus C naught plus Hadamard is a universal set. Yes.
Yeah. Okay. No, I guess okay. No, I think it's good. Yeah. Thank you.
Yeah, because I think the native gate sets on IBM devices is also C naught, Hadamard, and rotation, if I remember correctly. But yeah, there are a lot of combinations of these gates, and one of them is what is HSC naught plus T gate. Another is Hadamard and Toffoli, and then you can also have C naught, Hadamard, and rotation gates.
Okay.
Yeah. Okay, so now after laying all the initial groundwork of explaining the classical algorithms, which we have right now, the best classical algorithms, explaining a little bit of basics about quantum computing, I just want to now go and talk about where do I want to apply these methods and understand more. So my thesis was related to studying holographic gauge theories on the lattice. So for example, in my PhD, I studied some maximally supersymmetric gauge theories, which are related to some supergravity theory in some large n and large lambda limit. These are useful because they can lead insights, give you insights into quantum gravity. Just a second to put this down again. Okay. Yeah. So give you insights into quantum gravity from field theories and quantum any-body system. For example, the most famous example probably is the ADS-CFT correspondence, which relates a four-dimensional conformal field theory, which is supersymmetric with certain number of supercharges in the large n and large lambda limit to something which is supergravity, or for example, it's like the low energy approximation of quantum gravity. But this is not true just for 4-dimensional field theory or 5-dimensional ADS space. This was extended soon after the original paper, in this PRD paper, to P plus 1 dimension, where P can be anything less than 3. So we studied 1 plus 1, 0 plus 1, 2 plus 1 dimensional field theories using lattice methods, using Monte Carlo methods, to find some signal that whether it's holographic or not, and to test holography in some sense numerically. But the problem is these are all Wick rotated calculations, in the sense that when I use Monte Carlo, I work in Euclidean space. So what happens if you want to go to study real-time dynamics, or you want to compute some correlators in real time? Or say, for example, you want to look at things like chaos, or how chaotic the system is. Those things are not accessible as straightforwardly in the Euclidean picture. And in fact, we have no tools to study real-time dynamics of such strongly coupled field theories in higher dimensions. As I said before, one of the candidates is tensor networks, but even that is harder in higher dimension. So one of the things we can ask right away right now is, which is the simplest holographic model for which I can do a real-time evolution using some quantum resources I have? And it turns out that the simplest model is the SYK model, because, for example, even 0 plus 1 dimensional models like BFSS and BMN are very hard for quantum computers at the moment, and it's going to be harder in the next 1 or 2 decades. So that's why we started with SYK model, and we wanted to do something holographic. So let's look at that model. Okay, so what is the model? SYK model is a 0 plus 1 dimension. So there's just a Hamiltonian. So there's no sort of volume dependence, as we say in lattice field theory. Everything happens at a particular site. There are n fermions. And out of those n fermions, 4 of them, or say q of them, can act at a given time. So for example, in the figure you see, I have 8 fermions, which are labeled from chi1 through chi8, and 4 of them are interacting at a time, right? So these are just the 3 terms in the Hamiltonian. The number of terms in the Hamiltonian with 8 fermions and 4 of them talking at each time is just 8C4, which is equal to 70, binomial of 8, 4. So binomial of 8, 4 is 70. So there are 70 terms in the Hamiltonian. You just see 3 of them here. I've just shown 3 of them here. And all of them are talking with some coupling, which is random. And that is labeled by this J. So for example, if 1, 2, 4, 5 are talking, there's a coupling J, 1, 2, 4, 5, and so on. And that coupling is taken from some distribution, which is Gaussian, and it has some mean and some variance. And that's why it's sort of a random disorder model, because you have couplings which are taken randomly, right? So this model was initially written in some other form by Sachdev and Ye in 92, but Kitaev showed that this has some holographic properties, and then it became popular. Okay, so what are these chi's which you see in this Hamiltonian? So I've already explained that the Q in the Hamiltonian is the number of fermion talking at a particular time in the Hamiltonian. So we set it to 4. J is the random coupling, and then chi's are the fermions, and you can have, say, for example, n of them. And the chi's, which are the Majorana fermion, they satisfy this anti-commutation relation that chi I, chi j plus chi j, chi I is equal to delta ij. We can set the variance to be such that the j square in the variance term, which is given here, is set to 1. And this model, in the limit of large number of fermions, but taking the fermions faster to infinity than beta j, for example, in the limit which is given here in the last line, that n greater than beta j, much greater than 1, this model has several interesting features, such as it saturates the Lyapunov exponent, which measures how chaotic the quantum system is. So this model is interesting, and it is also related to, say, the dual gravity. It has a gravity picture, which is not as clear-cut as the one we saw before, for example, in ADS-CFT or P+1 superangles, but still has some holographic interpretation, in the sense that there's some gravity picture which emerges in the IR. at low temperatures. One of the first things we have to do if you want to study this model is map the fermions to qubits. And for that, since we are just have no spatial dependence, it's much easier. And those mappings are what we call as the usual Jordan-Wigner mapping. You can write down the chi's in terms of qubits. And this is written like this. So chi at, say, with index, with odd index will be mapped like this. Chi with the even index will be mapped like this. And you can write down the terms in the Hamiltonian. Now, the simplest case we can take is that we take 4 fermions, and 4 of them are talking at each time, right? So the number of terms in the Hamiltonian is just 1. So the simplest case is 4 fermions, 4 of them talking at one time, 1 term in the Hamiltonian. Note that if you have more than 4 fermions talking, then the number of terms grows like n to the q. Since we restrict to q equal to 4, we'll have a number of terms in the Hamiltonian growing like 4th power of the number of fermions. So the Hamiltonian is really dense. So for example, it's a very complicated Hamiltonian. And that is why we wanted to put to test quantum computer and see what we can do. And that's because usually when you see quantum computing papers these days, you have Hamiltonian, which will have at most 5 terms, 10 terms. But for n equal to 8, we already have 70 terms in the Hamiltonian, which is pretty complicated for the time we are in right now with the quantum hardware. Okay, so let's look at the simplest case because this gives a good idea to understand what is going on. If you didn't follow it completely at this point, it will be more clear here. So I'm setting q equal to 4, n equal to 4, and then writing the Hamiltonian. So the Hamiltonian is just j 1, 2, 3, 4, chi1, chi2, chi3, chi4. If I do this Jordan-Wigner transformation, chi1 can be written like poly x, Kronecker times identity. Chi2 can be written as y times Kronecker product I, and so on. And you can write all the 4 fermions. If you simplify them, just find that the Hamiltonian is a 2-qubit Hamiltonian. Because remember that if you have n Majorana fermions, you have to use n over 2 qubits. So it's a 4 fermion Hamiltonian, you need 2 qubits. And the Hamiltonian in terms of those 2 qubits are just given like minus j 1, 2, 3, 4 z times z. Now, the question is, if I have the simple looking Hamiltonian for n equals 4, how can I exponentiate it and compute the exponential of minus IHT? And to do that, we just need a simple circuit, which is given here. So if you have a Hamiltonian like this, and you want to do a quantum simulation, you have to write a circuit for that. And the circuit looks like this. So we know the gates from the previous slides. So the 2 gates in that circuit is just C0, controlled not, and the rotation gates. Rotation gates are just, so this is RZ rotation. So it's just exponential of poly Z with some prefactor, right? So the argument of that rotation gate is given by the time. What time do you want in your simulation, for example? What is the delta T you want? And this circuit is one trotter circuit. So for quantum simulating these models, one of the popular methods is the trotter-based method. So the trotter-based method is just saying that if you have an exponential of something, you can rewrite it as product of exponentials with some error. And that is exactly what it does. So this is one trotter step. If you do this n number of times, you can get to a time which is n times delta t, right? This is just one step of n number of trotter steps. So just repeat the same circuit n times. Okay, so if n is equal to 4, I need 2 C0 gates. So in the current era, we have the complexity or the cost or the problem of quantum simulation is related to how many C0 gates you have. So how many C0 gates you have, what is the depth of those circuits? So for n equal to 4, we see that you need 2 C0, right? So now a general question is, how many 2-qubit gates do we actually need to simulate the SYK model for any n, obviously? Like say, if I make n equal to 50, how is it scaling with n, for example? And for that, we have to solve this. And this has been well studied in the literature already, because people realize that this is going to tell us that how quickly you can reach quantum advantage or utility, like in this model. So this is the trotter-based method, which I mentioned in the previous slide. I divide the Hamiltonian as in n to the 4 terms, where each term is hj, where j runs from 1 to m, and m is some number proportional to n to the 4th. And then you do the trotter-based method, where you exponentiate this exponential of minus ist. You rewrite it as a product of some hj's, in which you're decomposing the Hamiltonian initially. And then there's some error, which grows like t square over r. So if you make r arbitrarily large, then you can suppress the error. So you need to take a lot of steps, and each of the steps will have small delta t, right? So the complexity basically reduces to finding how many gates you need per step. So in this case, we needed 2 C0 or two 2-qubit gates per step. How many gates do you need here? I just want to point out that this product formula, or the Lee-Suzuki-Trotter formula, which was first given by Seth Lloyd in '96, is just a corollary of this Hazen-Hausch formula. Hazen-Hausch formula is also known as dual BCH formula. So we all know BCH formula well from physics courses. If you do a dual of, you can take a dual of BCH formula, and then one of the corollary of that result is the Lee-Suzuki-Trotter, or the Trotter-based method, or the product formula. So the complexity, which is the number of 2-qubit gates you need to simulate, has been well studied in the literature, and people have obtained different results. But the thing I want to point out was that it was at least n to the 8th in this paper by Susskind and Swingle, and then it was n to the 10, 3 years before that. The last method is the most efficient, obviously, because it depends linearly on the time, and it is also depending only as 7/2 in number of fermions, much better than 8. Not much better, but better than 8, probably. Yeah, much better, actually. But the problem is the first two method uses the Trotter-based method, and this third is completely different. Third is something in the fault-tolerant era. Once we have quantum computers which are fault-tolerant, then you can use that complexity. But I cannot use the Babush result to do something on a IBM computer right now. So we had to play around with n equal to 8. And then we improved n equal to 8, n to the 8th scaling to n to the 5th scaling in our paper, which was one of the work we did last year. And with n equal to 5, it just reduces the number of gates needed, and you can reach to larger n faster. So the complexity we find.
Question.
Yes.
So n to the 8 because of the coherence time of your devices, or just because that's a nice number you chose?
What is a nice number? Sorry.
So n to the 8. Did you choose n to the 8 because of the coherence time of your?
No. So this is no, this has nothing to do with the coherence time. This is asking the question that if I have a Hamiltonian and I want to simulate that Hamiltonian, how many gates do I need?
It's not a choice.
And
Hello.
these people found in this paper that you need n to the 8. So the scaling is n to the 8. For example, if I double the number of fermions, the cost becomes 256 times, because it goes like n to the 8th, right? So what this paper said was that if you have n equal to 20, but you want to do n equal to 40, the number of gates will change by a factor of 256, even though the number of fermions is changing by a factor of 2, if t and e are fixed. What we said was that it is not increasing by a factor of 256, but it's only increasing by a factor of 32. And that's all it is. Is that clear?
Okay, great. Yeah, thanks.
Okay, thank you. So how did we reduce the number of terms from n equal to, how did we reduce the number of gates from n to the 8th, which is a bad scaling because more resource needed, to n to the 5th? The trick we use is well known in the in the computer science literature, or even in quantum computing computer scientist literature, which is basically a simple physics result, which says that If you have a Hamiltonian and you're a little more careful in splitting your Hamiltonian, then you can really make it much more efficient. Because remember that the trotter is all about splitting the Hamiltonian here and then exponentiating all those terms and taking the product of that. So how do we break the Hamiltonian? If you break the Hamiltonian such that you group together the terms which commute with each other together. So for example, Hamiltonian might be broken up into 100 terms, but out of those 100 terms, there might only be 5 or 10 groups where all of the terms are commuting with each other. So the goal of reducing the complexity then is mapped to a problem of finding the optimum number of clusters. And once you have found the clusters where everything commutes with each other, then you can simultaneously diagonalize that circuit. And if you can simultaneously diagonalize, you can also find the time evolution operator, which can be implemented for the entire cluster. So that is what we did and improved the time. So what was the cost we got? I showed you that for n equal to 4, there was just one term in the Hamiltonian, which is given by Pauli strings. There's just one Pauli string. There's just one cluster, and you need 2 qubit gates. You need 2 C0, so you need two qubit gates. For 6, 8, 10, 20, you can go all the way to whatever n you want. N equal to 100, I've just shown n equal to 20. For example, n equal to 20, SYK model needs about 20,000 C0 gates, right? And this is, yeah.
Can you maybe say a little bit more how you found these numbers? So on the previous slide, I think you said there are some algorithms.
Yes. Yes.
Can you more about?
Yeah. So the way we found this numbers is that you rewrite you first make the Hamiltonian, then you so for example, you first write your H, and then you take based on the number of fermions interacting at a time and number of fermions, you write your H in terms of Pauli matrices. Once you rewrite in terms of Pauli matrices, then you find which of the terms are commuting with each other, and for that we have to use some algorithm which is known as the graph coloring algorithm. Because if you want to find out, so for example, think of a graph, and then you want to find out which links commute with each other or something like that, then you have to use something called a graph algorithm, graph coloring algorithm, which colors the graph based on whether the neighbors commute or not commute. So there are well-known algorithms. We used an algorithm which is called degree of saturation of a graph. So it's very popular, well-known algorithm proposed in the 70s. And once we use that classical algorithm, it gives me the number of clusters, basically. That, okay, this many clusters, and then it puts all the Pauli terms which are commuting with each other in those clusters. So that is step 1. Once you have those clusters, then you take the clusters one by one, and then you find out the diagonalizing circuit for those clusters. You diagonalize everything in those clusters by using some unitary transformation. Once you do that unitary transformation and diagonalize everything in that circuit, then you map it to a quantum circuit like we mapped this term here. It was easy in this case because we can do it by pen and paper. But for n large and other things, we have to write a code. And then you can find the diagonalizing circuit for each cluster. Once you have a diagonalizing circuit for each cluster, then you just add them to write down the time evolution for the entire Hamiltonian.
Do you know if your result is optimal?
So this is a very good question. So if we talk about the optimality of this complexity, then we have to look at the number of terms is growing like n to the 4th, right? So I would say that the optimal should be close to n to the 4th. We find n to the 5, but maybe, yeah. So the optimal, I would say, should either be n to the 4th or less than that. But n to the 5th, I cannot say that it's optimal. I would say it's very close to the optimal, but there's no proof that what is the optimal bound for a random Hamiltonian like this that I know of.
So these algorithms that you mentioned, there is no clear estimate of how approximate they are as a function. So you mentioned.
So that approximation is given by epsilon. So epsilon is the difference between the actual unitary and the unitary you construct using these trotter-based methods.
Cases approximate. I don't think. Is your number of clusters optimal? Do you know that?
Oh, number of clusters, reducing the number of clusters is an NP hard problem. So you cannot find the, so as n increases, so for a small number, for these cases, it might be still possible, but it's a, so for example, finding optimal number of such clusters is a well-studied computer science problem. This is general NP hard. So finding the optimal number for n, which is very large, is, yeah, it's not a.
Okay. No, my question was about that. So is there, and I guess Vishnu's question was also that. So how close are these number of clusters
Oh,
to the
yeah. So, okay, let me repeat it. You are asking how close these number of clusters is close to the lower bound or something, optimal value.
Yeah. And also maybe a related question is it obvious that the minimal number of clusters is the best? Could it perhaps be that, because ultimately you're counting in terms of the gates complexity, it's maybe not completely obvious that the minimal number of clusters would also correspond to the minimal number of gates. I'm not sure, but that sounds like something reasonable, but I'm not sure it's true.
Yeah, so I did not explore whether the clusters, which was, so the way I did was I used 3 different algorithms like DSATR and the other ones, which is inbuilt, and then found the number of clusters using them. I just took a minima of that. So there might be some optimum number which is much smaller than that, but this might not be the smallest number of clusters. You can find probably until n equal to 20, this is probably the optimal because it's a small scale problem. If you go to larger n, it might be hard, but for n equal to 20, I would say the optimal might not be like 200. It would be like 243, 242, 240, and so on. But those doesn't make a lot of difference to the, it just increases the gate count by 100 or 200, order of hundreds, while we are order of 20,000 already here. So yeah, I think it's just the optimal number of clusters can be reduced, and it's also not very obvious that if you find there might be some cluster which is great in number but has less gates and so on. But those problems, I have not studied those problems.
Okay, thanks.
Yeah. Okay. So everything I talked about until now was related to the dense SYK Hamiltonian, right? So the dense SYK Hamiltonian is where you have the number of terms growing like n to the 4th. So if there's a 4-body interaction, the number of terms grows like n to the 4th. But this is already hard for, there's a lot of terms. So what people started thinking about in 2020, I guess, was is there a way that you can sparsify the model and still retain holographic features? So note that the whole point of doing SYK is that it's holographic. So now I can ask, okay, this SYK Hamiltonian is holographic, but now I start removing the terms randomly. So I write down the n to the 4 terms. I start randomly removing the terms from that Hamiltonian. And this is what is called as the sparse SYK model. This was first studied in this paper by Susskind and Swingle, and the other paper, which is July 2020 paper. But this was also studied recently in this paper from 2 months ago. And the whole point was that it turns out you can actually sparsify the model quite a lot. In fact, for n greater than 40, you can throw away 90% of the terms in the dense SYK Hamiltonian, and you can still have reasonable holographic connection. In the sense, how do we say whether the model still has reasonable holographic connection? You compute what is known as the Lyapunov exponents. So you look at a 4-point correlator, you compute, look at the growth of that correlator in certain time regime, and then you see whether you find the Lyapunov exponent, which has a bound, which we know. So if the bound is being saturated, if the Lyapunov exponent saturates that bound, then the model is still holographic. So taking out 90% of the terms seems like a lot, but it still has a lot of interesting physics left. So for that model, I studied the complexity and did the same thing, and using
can I ask one question about the sparsification? So, can you kill off terms like randomly, or do you have to be careful how you
So,
kill?
yeah, that's a very good question. Till now, all the papers have killed the terms randomly. But I have this proposal which is not written up, where I say that if you are a little more picky in killing the terms, then you can even do much better. Like, but that is I don't think anyone has looked at the sparse SYK, where you choose which terms to kill and which terms to keep. Right now, everything is done randomly. At least all papers, 2000, all these 3 papers, 4 papers are randomly, yes.
Okay.
So
Yeah.
question, the number of terms you're left with, 0.1 n to the fourth is still a large number of terms. Is there a way to parametrically reduce this in n?
Reduce this in n. So this coefficient, so for example, the k which we choose is related to the n by this equation here. K goes like sorry, k is fixed, for example, but k in the dense SYK model goes like n to the cube by 24. So now you're saying that can I change k based on n? I don't think people have explored that. They want to fix the average degree of the interaction, which is number of terms divided by n. So it's like you want to fix that number, but maybe you can change k as well based
So
on
no,
n.
my question is really that, okay, so you have n to the fourth terms typically, and you're
Yeah.
reducing this by 90%. So you're left with 0.1 times n to the fourth terms.
Yeah,
That's still
90%
generically large though, right?
Yes, absolutely.
So can I reduce this n to the fourth to n, some other power of n? Would that be, I mean, is it the thing I'm reducing by is some small number times n to the fourth? That's still a fixed number. So the
Yeah,
scaling is still n to the fourth.
Okay, so I think the point of confusion, I understand the point of confusion in your question. So I'm saying that it reduces the term, for example, at n equal to 14 by 90%. But if you give me an n of, say, 60, then the number of terms reduces 99.5%. So what I really want to say here is that it reduces by more than 90% of the terms. I'm not saying that it reduces by 90%. It reduces by 95% for n equal to 16. You can calculate that number. It reduces by 99.5% for n equal to 100 probably.
So, okay, I understand. Should I should therefore still think about this as some reduction with the same scaling with n?
Yes.
Okay.
Yes. Yeah, I just should have added one more word, that at least 90%. I just said more than 90% maybe. Yeah. So that sparsification is like, yeah. So these people studied that and then found, okay, so now it's like the SYK model is pretty complicated, a lot of terms. It has now been reduced to a point where it's very sparse, and much more things can be done. And now the scaling is down from n to the 5 to n square, which is probably you can reduce it even further. The dependence on k is not that great. And then you can use a second order Trotter method to even reduce the t square from this approximation. So note that this is t square because I'm using the first order Trotter method, which is shown here. You can use a second order Trotter method, and the t dependence is reduced even more by 3/2 and so on. So the complexity really reduces a lot. So the argument is that this is the simplest holographic model for a quantum computer. So whenever someone wants to study holography, the model, they cannot study 0+1 BFSS, BMN. It's like out of sight right now, but maybe sparse SYK is the first place where we'll compute something with holography, which we cannot do using classical computers after maybe 5-10 years. Okay, but we studied dense SYK model. We can obviously could have studied sparse, but at that time we wanted to look at the dense model. One can do a sparse SYK, but I don't think there's much point here now doing that. But yeah, for dense SYK on quantum computers, we computed something called a return probability. By the way, how much time do I have?
Sorry, Raghav, I was about to mention, maybe if you could talk about 5 minutes.
How do I have 5 minutes, 10 minutes, 15 minutes? How much time do I have?
Yeah, you have about 5 minutes.
5 minutes.
Yeah,
Okay.
sorry for the questions. I mean, I guess people can feel free to leave if they have to leave. If you want another 10 minutes, that's also fine. Actually, we're happy to keep listening. So if people need to leave,
Yeah, I'll take. Yeah, I don't. Yeah, yeah, I will lose my energy of talking, so I will not talk for more than 10 minutes. I'll continue a little faster now.
okay.
Yeah. Okay, so we compute two things. The first thing we compute is the return probability. Return probability is simple. You start with some state, you act with a unitary operator, and you get to a final state, and then you take an overlap of the final state and the initial state. So, for example, n equal to 4 circuit is shown here. N equal to 6, for example, will need 32 qubit gates, as was shown before. This is the IBM chip we run on. For example, you can see 127 qubits lined up in some special topology. If I want to do n equal to 8 SYK model, I need 4 qubits, and the 4 qubits are marked in the reddish blobs. So you take those 4 qubits and do the simulation. One of the things interesting about this topology is that there's only restricted neighbor available to a given qubit. So for example, the maximum valency or neighbors of a given qubit is 3. And for SYK model, this is a problem because SYK model is an all-to-all interacting model. So for example, if I want to connect the first qubit to the 15th qubit, because that will have a term in the Hamiltonian, it's a problem. That is why maybe for SYK, IBM chip topology is not very useful, but for other models of interest in physics, there's always nearest neighbor or next to nearest neighbor interaction, and you're still okay. We take results for return probability using IBM devices. These are 5 instances of the model labeled as A, B, C, D, E. And the black dashed line you see is the result from my laptop. The red dots you see are the results from the hardware. Just a second. Annoying sound I am getting. Okay. So the first 5 instances are the ones from the 5 instances of the model, because note that SYK model is a disorder average model. So you can take different instances of the model when you take couplings from some distribution. So the black is the lines from the laptop, the red is the result from the IBM device, and then green is the mitigated results. So what do we mean by mitigation? You take the results from the hardware, but that is not that is not accurate enough. And then you do some sort of error mitigation. You try to do post-processing, and that is what we call error mitigation. And then you try to find out a scheme, and then you see that the results agree, right? So for example, the black dashed lines agrees very well with the green data points. And the circuit on the rightmost side, rightmost point used about 300 ECR gates. So ECR gate is another type of a gate which is related to the C0 gate and thing like that. It's one of the universal gate set available on these IBM Eagle processors. So ECR gate, about 300 ECR gates. So 300 ECR gates is a lot, is almost the state of the art at the moment. People did Schwinger model also on something like 330 or 50 gates recently. But we also did state of the art probably in this model. So we did a lot of error mitigation. I don't want to go into details, but the error mitigation is based on some of these papers. You can refer to these papers. It's called C0 only mitigation or self mitigation. So we do 3 layers of mitigation. We do the 2 which is inbuilt into the Qiskit and IBM devices, which is called M3 and dynamical decoupling. So M3 is just a matrix reduction process. So you measure some probabilities, it reduces the matrix dimensionality and then focuses on that subspace, and that is M3. DD, dynamical decoupling, is that there are some qubits which are left untouched during a simulation. So dynamical decoupling applies pulses to that, so they're not sitting idle for a long time, because if they sit idle, they can get decohered with the computations or from the circuit, and that introduces errors. So we use M3, DD, C0 only mitigation, and self-mitigation to obtain results. How do you do self-mitigation? So self-mitigation or C0 mitigation, the basic idea is that you have a physics circuit which you want to run, and then you make an exact same copy of the circuit and run that circuit. And then on the other circuit, you see the probability of the error happening. So for example, if it was a real error-free world or error-free quantum computer, then the probability of error will be 0, right? But on a real quantum computer, the error of probability is some p, which is finite number. Once you get that p from the mitigation, you can use the theory from quantum information literature, which is called a depolarizing channel. You can put some numbers in that, and then you can correct the expectation values. And that is exactly what is happening in these green points. So we are using the C0 only mitigation and using this depolarizing channel to estimate the probability of error and then correcting the expectation values based on that. So this was the first thing we computed, which was the return probability. There's another thing which we computed, which is the more interesting thing, which is obviously related to the 4-point correlators. So for SYK model, you can rewrite 4-point correlators of some operators, and then you can look at how it grows. For example, there are different time scales called dissipation time, scrambling time, and you can try to find out what the Lyapunov exponent is. If you are at very large n and at very small temperatures, you'll find that the Lyapunov exponent saturates the upper bound, which is given by 2 pi times temperature. And even though we cannot go to very small times or large n, we tried to compute the OTOC on the quantum computer. But computation of OTOC on quantum computer is not straightforward because this is a 4-point correlator and it's out of time ordered. By out of time, I mean it has an unusual time ordering, as you can see in this expectation value. The first operator is evaluated at t, the other one is at 0, and so on. But there are a lot of protocols people have worked on. One of those protocols is a randomized protocol. And we use this. What is the randomized protocol? So the randomized protocol is just, it breaks the problem of computing the 4-point OTOC as a statistical correlation of two observables, which is mentioned here. For example, if you want to compute a 4-point OTOC, this protocol just says that you can compute WT on some random state, and you can compute some other observable V dagger WTV on the same random state. And then you can take a lot of random unitaries and then find the statistical correlation between them to get a proxy for the OTOC. And this is the randomized protocol which was proposed in this paper. There's a paper on other OTOC on quantum computers, and for that you can see this paper by Swingle here. Okay, so the randomized protocol breaks the computation of 4-point function into computation of two observables or measurements of two observables. So that is given in A and B. In A, we start with some initial state K0. We act with a random unitary from the Haar measure. And then we do the time evolution using Trotter-based methods to compute something which is WT. And on the right side, you compute some other ingredient you need for OTOC. And using both of these, you can compute the OTOC. Right? So we computed OTOC on the same 127 qubit processors, which is IBM Cusco and IBM Nazca. And for n equal to 6, the results are shown here. We go to a depth of about 260 ECR gates. And in this case, the black is still the dashed line. Note that the last panel is the disorder average over the first 3 instances. So the black and the blue are the exact results, and the one one in red is the result from the device, and then the one in blue is from a noiseless simulator, for example, from Qiskit. So you can do the same thing on a Qiskit, you can do the same thing exactly, and on the hardware, and we compare all these, and the agreement is pretty reasonable for a complicated observer like OTOC. Okay, so this was all at 0 temperature, ideally, but the problem is I promised you at the start that SYK model is only holographic when beta is very large or temperature is very small. So, sorry, in this initial thing, everything here is infinite temperature, sorry, not 0 temperature. We want to go to 0 temperature, very small temperatures, and for that we have to go away from the infinite temperature limit. I just want to say that the infinite temperature limit is easier for quantum computer because computing observables in this limit is easy because the density matrix is just identity up to some normalization. So if you compute the density matrix with beta equal to 0, it's just identity matrix and it's easier. But if I take finite beta, the calculation becomes harder. We run into the issue of how can you compute thermal states, for example, using a unitary evolution because thermal state is a mixed state and so on. So now we are trying to extend this work to finite temperature SYK using variational methods. So variation methods are another class of problems which are used to find out the ground state of a given Hamiltonian. But this is usually done for 0 temperatures, but there are ways in which people have extended this to finite temperatures, for example. And finite temperature VQ is still an active area of research, but we are trying to use an algorithm and then trying to construct the cost function, which is the free energy, trying to minimize it. And once this is done, so this is a unitary circuit. I'm not claiming that I'm making a thermal state, which is a mixed state. I'm claiming that I can get an approximation to the mixed state or thermal state as a superposition of many 2 to the n basically states which are all pure. So it's like you write down you find out the probability, you find out the state. So 0, 0, 0 has some probability, 0, 0, 1 has some probability, and then you take a combination of that, and that gives you an approximation of the thermal state. So this is some work we have been doing for SYK model at finite temperature with some folks at the lab. So using this, we are able to go to n equal to 8, 10, 12 for dense SYK. These are preliminary plots, but hopefully we'll write this up soon. Yeah, and then you can compute free energy, Hamiltonian expectation at some finite beta entropy. And we have been able to create these states with very good fidelity. So fidelity is a measure of how close the state we are preparing using this circuit is to actual Gibbs state or thermal state. And we see a reasonably good fidelity with that. So this is upcoming work. And I'll just summarize now. I just want to say that with this talk, I just wanted to emphasize that we are entering an era where we can compute few things, even if those things can be done quickly on the laptop. Exploring these toy models will hopefully teach us better algorithms, methods, and understand the computational complexity in a better way. It is instructive to see that if we characterize the noise in these quantum devices, we can get reasonable results. But obviously, error mitigation was an important part. If you just take the results from the hardware and put it against the exact, you won't likely see an agreement. So there's nothing which we can do today on quantum computers which cannot be done on laptops, but hopefully this thing will change in the next couple of years, and that is where we'll cross that era basically. And then there will be a lot of computations in at least time evolution and other things where it cannot be done on laptops for sure, and definitely not done on supercomputers either. Use of hybrid discrete systems are important to have study physical models, because what I considered was a fermionic system. So for quantum computers, fermions are easy because of the Pauli's exclusion principle, because it restricts a number of states. But if you have a bosonic degrees of freedom, all of them can be the same state. It's like infinite reverse space. And then encoding bosonic degrees of freedom into qubits is hard. So for that, the continuous variable approach or the oscillator basis or the photon basis photon approach might be better. We are still trying to find out problems where quantum computers would really have the edge as far as physics is concerned. And that is an important direction. So with that, I would like to thank you for your attention.
Thanks, Raghav. Are there any questions? Yeah. Which mic? I think all the mics should work, but they're just not that good. Please start.
Okay. Hi, Raghav. Thanks for the nice talk.
Hi.
So I just wanted to check a lot of the data that you showed. So this data was not from the simulator. This was from the physical device itself.
Yeah. The red points were from the physical device. There's no simulator in that.
Okay. And then I wanted to check. So what circuit depth did you have? Because I mean, if you're solving problems at this scale, your circuit depth is quite limited by the coherence time of your device.
The circuit depth is about 200, between 270 and 300, 2 qubit gates.
Wow, and your data looks quite pristine.
Yes, that's because we do 3 years of error mitigation. And I think it also has to do something with the model, I guess. But I think if you don't do the error mitigation, the data doesn't look that nice. So let's look at. Okay. So the red points are off from the exact curve, right? It's like there's no agreement between the red and the black ones, literally at some random points where it becomes too small. So I would say that the self mitigation we did was the real difference.
Wow, it's still impressive. Then last question, when you evaluate your return probability, because I see that's the game you're playing, right? You're creating your exponential for your Hamiltonian, and you keep evaluating this return probability. So are you performing this like a hybrid algorithm, or are you running everything like single shot for every t that you're interested in?
Yeah, so the way we compute the return probability is that we are starting from the state, which is all spin up. So for example, for n equal to 6, you start with the state with 0, 0, 0. Then you have your trotter circuits. So now, for example, if I look at these diagrams, you see that there are points at t equal to 3, t equal to 6, t equal to 9, t equal to 12. One of the things about self-mitigation is that you can only do even number of trotter steps because of the way the mitigation technique is built. So for example, in these plots, we set the trotter step to be 1.5 and then do 2 steps. So for example, you start at t equal to 0, where the probability is obviously 1 because the states are the same. And then you write down the trotter circuit for 2 trotter steps. And you have that file. You put that quantum circuit to the hardware, compute 8,000 shots, get the measurements out of that, and then you compute the overlap with the 0, 0, 0 state. You get the red point. Once you get the red point, you do post-processing using self-mitigation and get the green point. Once you go to t equal to 6, you have to use, for example, you have to use 4 trotter steps, right? 1.5 times 4. So you build a circuit for that, 8,000 shots, do the same thing. And similarly for all other points. So that's why t equal to 12 has number of gates, which is about 300. And that is what you need for 9 trotter steps with n equal to 6. Not assuming connectivity. The numbers I've quoted here assumes all-to-all connectivity. But if you put n equal to 6 SYK on a IBM computer, you'll need more than 32 qubit gates because you also need swap gates and things like that. So you do the same thing, and then that's how we did it.
Okay, any other questions? So maybe I'd like just to ask, when you did the complexity scaling, did you include Q, the number of fermions?
I cannot hear that properly. I just heard the first sentence when I did the complexity scaling. After that, I couldn't hear.
You include Q, the number of Majorana fermions in a term in the Hamiltonian.
Oh, you're asking about the dependence of complexity on on Q. Is that correct?
Yeah. Yes.
Yeah. So the dependence on the complexity, I just didn't include that because that is order 1. If you have Q, which is not very large, say 4, 5, then it's just order 1 number. It just obviously if you take Q equal to 100, and then you have to the complexity. This is actually, if you want to look at that, it's mentioned in this paper. So the dependence Q was worked out in this paper. Which paper was that? This paper. I think they worked out the dependence on Q on this 2008-02303.
Okay.
But this is order 1. I'm at Q equal to 4, so it doesn't really affect. It's like 4 to the power. Like it will be, the prefactor will be 4, or it's the power is not greater than 1. That's what I'm saying. It's like 4 to the 0.7 or 4 to the 0.9 or 4 to the something 0.95. It's like it's a prefactor of 4.
Okay, cool. And one more question. I think you mentioned this all the way at the beginning of your talk. You said that quantum advantage could be achieved when n is 65 or something.
Oh, that's right. That's right. Yeah. Where did I say that? Oh, I said that somewhere, so I don't need to go. I remember what you are talking about. So what I'm saying is that people have worked this SYK model up to my understanding. There's a paper by Douglas Stanford and other people, which is a PRL from 2020, or 21, where they computed OTOC or Lyapunov exponent up to n equal to 60 or 65 or something like that. What I'm saying is the quantum advantage can only be reached if you can go to n equal to 70 or 80 and you can compute OTOC. So that is the limit where the quantum computers will be better than the classical computer for this problem.
I see. And the 127 qubit machine, how many?
Yeah. The problem is not the number of qubits, as I mentioned. The problem is that if I take the dense SYK model and I put it on this chip, even if the model is, say, needs 40 qubits, it can be put on this. This is not a problem. But the problem is this topology does not talk. It's like it's highly unsuitable for the all-to-all interaction like that. Because suppose you have a 30 qubit SYK Hamiltonian, and you will definitely have a term in the Hamiltonian where the first term will be talking to the, say, 30th term, right? Because this is all-to-all interaction mode. Now, if you want to connect this end of qubit to, say, 30th will be something like this, you have to use so many swap gates. It's going to increase the gate count and the reliability of the computation, like pretty much. It'll make it very hard. So one of the things which I'm saying is that forget about the dense SYK model, look at a sparse SYK model, and don't throw terms randomly away, but throw the terms randomly away based on what their numbering is and what they are, whether they are commuting and all with each other. Because if you do that, then it becomes much more efficient for devices like this. But there are other devices like, for example, iron-based, where everything is connected to everything. So if you use the quantum computers from Quantinium, they have a 30 qubit machine where all the qubits are talking to each other.
Okay.
So
So then it's can be avoided.
Yes. So I told those people to like use those machines for SYK, because that's probably they'll get much better results than I have for n equal to 8, because they have complexity.
So you're saying, so you're not random elimination of terms. So that you do that with the objective of matching with this IBM processor topology. And so your objective in when you sparsify is to make it more suitable for the IBM processor.
Yeah. But what I'm saying is you can sparsify keeping in mind the topology or the connectivity of the device also. You can sparsify along that. There's nothing else.
I see. But also said that is actually that sort of non-random sparsification. It is also somehow better than the random sparsification. That seems like a lucky coincidence.
Yeah, I don't know. I don't know what to say about non-random sparsification and random sparsification.
Okay.
I started thinking about this, but then I have to I can think more, but then I should move and look at other models, I guess. It's just but I think there's a lot of other interesting things you can do in SYK model, I guess. But yeah, I think in 5 years or something, people are going to run like these experiments a lot on these devices, like Quantinium, IBM, and things like that. So we'll get more results in coming years.
Yeah. Okay, great. Thanks a lot again for the talk. I think there are no more questions. So it's a shame that we couldn't have you here, but hopefully.
Yeah. Hopefully.
Taking the time on this.
Yeah, thank you so much, Sam, for setting this up and all the questions. Nice questions. Thank you so much. Bye.